All right. Thank you, everybody. Firstly, I just want to apologize that I'm not an ecologist. I'm an engineer by training, and I'm a professor over in civil engineering, so I work in fluid mechanics. And so a lot of what I do sort of crosses over into different fields, so it's very sort of complementary to the science. And so I'm starting today talking about environmental robotics. And I'm going to start with a quote from Walter Munk. And just a quick show of hands, does anybody know Walter Munk? Good to see a couple people do. So Walter Munk, well, he published for over 50 years and died just this year. I think he was 96 at the time, somewhere around there. He was at Scripps. And he said, advances in oceanography are dependent basically upon new kinds of instrumentation. The future of our science will be sterile unless we can continually find new things to observe and new ways to measure them. And so he coined this term, a century of undersampling. And I think this is also true in limnology. So limnology is sort of the poor stepchild to oceanography. Oceanography, we go out and we can fund large programs, large ocean programs, and limnology is very hard to adopt new technologies and new platforms, partly because of the cost. So that's part of one of the challenges. And then the other part is sort of the advantage of underwater robotics is that we can sample on an ongoing continuous basis, but you're also able to deploy them in hazardous conditions. So typically conditions when you wouldn't send people out on a ship with a water bottle to collect a sample. You can send a robot instead. So I'm going to start a bit as well by talking about the complexity of the problem we're facing. So here, cultural eutrophication. So this is the images we've been seeing at Lake Erie over the past decade. So addition of chemical nutrients lead to complex spatial variable algal blooms. These changes drive a reduction in oxygen in the underlying layers. So then it drives the overall ecosystem dynamics, changing the ecosystem dynamics. But in addition, one of the things we're starting to see now is something we're coined a couple of years ago, climatic eutrophication. So through climate change, the physics of these lakes are changing. So one of the things we're seeing, for example, in Lake Tahoe, where we do a lot of work, is that the actual warming season, the stratification season is lasting for longer. So that's driving a higher internal phosphorus loading. And so the turnover of the lake is being reduced. So the actual oxygen replenishment to that deep water now only happens, well, it happened this year for the first time in a decade, where it used to happen on a yearly basis. So the dynamics of the system is changing. And so is changing in Lake Tahoe? Could it be changing elsewhere? What are the implications for the dynamics of the system? And the changing ecosystem function also allows invasive species to come in. So you're getting changes in nutrient loading, producing long-term ecosystem change. And this ecosystem shift also allows these invasive species. For example, this is Corbicula flumina, Asian clam, that's now well established in Tahoe. And so this has been driven because they can survive in a warmer water. And they can survive in the nearshore habitats. And so I saw somebody with a Keep Tahoe blue shirt on in the front here. So this is the past conditions. So this is a picture collected by Goldman sometime mid-'80s. And this is kind of the new reality, that frequently we're seeing periphyton and metaphyton growing around the lake that may or may not be linked to Asian clam. So you can kind of see one of the little dead clam shells there. The direct causality is not necessarily shown yet, but this is one of the things we're trying to understand, is how do we look at the dynamics? And then also, and it's great to see some of the stuff from Randy, earlier on Clear Lake. So this was a citizen science picture. This is somebody just sent us a picture of something they saw from their deck, basically. So this is 2016. So climate change is driving the frequency of these harmful algal bloom events. And so this points to a need to be able to use sensors, so developing new SON technologies and new platforms, to go out and do rapid environmental assessments. And this is where sort of I start tying in the engineering with the science. Because part of the problem are the scales of observation. And so key sort of stuff is sort of right down, much smaller than what I'm talking about. But basically you're doing a trade-off between scale and resolution, where we have satellite imagery giving us the football stadiums, the 300 by 300 meter pixels. And then you start getting into drone work here, which we're starting to see more and more of. And certainly that's something that our group does work with a little. And then down to your boat sampling. So this is where you're going out and grabbing samples. And then autonomous underwater vehicles, where I spend a lot of time doing work on. So it's the trade-off of how much can you cover versus what's the resolution that you can cover. And then there's also a temporal effect to factor in. So can we put out long-term robotics? Can we put out long-term monitoring stations? How do they complement existing data sets? And how do we marry them all together? So autonomous underwater vehicles, to my students, I like to describe them as pickup trucks. That basically it's a propeller that carries around a torpedo, but then you can start equipping it with whatever sensors you can dream up. And so commonly there's a tight coupling between AUV manufacturers and instrument companies. And so some of the typical ones that we've seen are instruments that can measure physical properties. So you're looking at CTDs, sound velocity probes, Rockland turbulence probes to measure dissipation in the water, chemical properties such as DO, seabird pH, Satlantic nutrients, optical backscatter, measure chlorophyll, phycocyanin, CDOM, turbidity. These are commonly typically available from wet lab. These platforms have also been heavily used for imaging using sonars, so side scan sonars and multi-beam sonars. So you can configure it any way you want. So this is basically, we configure it and then we turn around and deploy these. AUVs are generally the duration of several hours for a given battery, so your scale of resolution is relatively small. You can cover about, on a given battery pack, sort of between 20 and 80 kilometers, depending on your type of vehicle. So we're going to jump out here. So another type of vehicle is called a glider. This is another type that you can put out for a longer term. And I'll just talk to this in the background. So gliders, instead of being a propeller that are driven around, basically have a fixed hull with an oil bladder inside. And you're changing the ballast inside, and so it's a buoyancy-driven engine. So instead of driving in a straight line, now it's driving a sort of a seesaw pattern or yo-yo pattern through the water column. And so you're able to now develop a much better appreciation of what's happening through the entire water column as you go. Back. So the advantage with this is that the vehicle will go along and periodically surface and transmit data back to wherever your host server is. So when we're running these, we can put them out for several weeks to a couple of months at a time. And so we can operate from anywhere in the world. And we generally have rotations. Students will be rotating through, taking turns of who's on point running the vehicle, because it can surface anytime during the night. So when they're on call, it's a little bit stressful. But it goes much slower because it's all about how much range can it do. So they joke around about half a knot on half a watt. So being able to cover longer range is sort of the goal of this. So one of the early studies we did up in Lake Tahoe, this is with an AUV, not a glider. So here in 2009, we completed 105 kilometers of shoreline in 8 days. So the scale of synoptic study that you can complete with robotics is way beyond what you could do with divers on a transect. Now, we had to still use divers as a complementary validation of our imagery. So here's a typical image. So basically, this is dead shell matter. All these little white things are dead shell matter as the Asian clams come to the surface and flip open. And we're using this. We wrote basically a detection algorithm.
If you write anything on your computer, you need to get Grammarly.
I write pretty much all day, every day, and Grammarly makes my writing better.
As a student, I like that it's free. It actually is
Sorry about that. Right there. Yep. So we wrote this algorithm that could basically scan through and count the number of dead shells. And basically what we then did is then ran diver transects to correlate live shell matter to dead shell matter. So doing these sort of complementary studies enables us to generate much larger synoptic views of what's happening in these systems. So here's a synoptic view of Lake Tahoe. So this basically, here's all the shoreline of Lake Tahoe. Blue was non-detects with the AUV. Red is where we knew we had Asian clam at the time. And then these oranges were actually where we thought we had new detects. Basically, these were all false positives after we went and did diver validation, except for this area where we actually picked up a native clam species. And then some here at the bottom that was actually more extensive than our original predictions of where these were using diver predictions. So being able to achieve synoptic views is one of the tools of using vehicles like this. The other thing, and we've seen this before already today, is validation of remote sensing. So here, like Randy was saying, is each of these pixels represents 300 by 300 meters. So how much variation is there actually within a pixel? So if you think about the AUV travels at about 2 meters per second, so about 4 knots. It samples at about 1 hertz, so you're roughly getting a sample about every 10 centimeters. So if you start thinking about that in terms of how representative is that one sample that you're getting when you're scooping it out of the water, using a tool like an AUV to be able to transect through gives you a much stronger validation of what that variability is. So now I'm going to jump continents over to a study that we running over in Lake Geneva last summer. So here, this is chlorophyll A detection from remote sensing. And what they're seeing is basically 2 large counter-rotating gyres. And these gyres have basically upwelling associated with them, so bringing nutrients up from the bottom. And they're seeing high areas of chlorophyll development in the center of these gyres. So what we ended up doing is trying to use a glider. So trying to understand not just what's happening at the surface, but what's happening at depth. So we set up a series of ADCP moorings, so acoustic Doppler current profiling, and basically across this gyre. And then we spent a good portion of the summer running a glider through this area to try to understand dissipation and the amount of energy associated with it. So to get to dissipation, so one of the things we do, in addition to trying to develop new platforms and try to develop new applications for platforms, is use new sensors. So this is a dissipation probe. Basically, it measures the turbulent dissipation within the water column. So we're trying to understand the energetics of the system. Because one of the hypotheses was that it's the energetics of the system that's contributing to how well the chlorophyll or how well the phytoplankton is doing within the water column. So we then started running profiles. This was ballasting the vehicle, getting it ready to go. And then we went into the lake and started doing large amounts of profiles. And so one of the things we were doing here, so here's a little cartoon of where we're running back and forth in sort of a seesaw pattern and trying to couple this to moorings. And what we saw, and so here's the boundary zone. Basically here, for those of you that looked at dissipation before, this is log base 10. So red is 10 to the negative 7 dissipation, which is relatively high, which is sort of approaching ocean levels. And then 10 is basically quiet, so there's no real motion down there. But along this, the boundary zone of the lake, we're seeing a lot of enhanced dissipation rates. So trying to understand these enhanced dissipation rates and throughout the water column, trying to understand mixing patterns, these are all things that we can get to with multiple platforms. And this is some of the ongoing work that's currently happening in Tahoe as well. So we know we hit enhanced dissipation along the benthic boundary layer, and this could potentially be resulting from internal wave migration. So it's the physics of the lake that are basically driving oscillations within the lake and can drive respiration along much deeper than we initially expected because of the large physics dynamics of these systems. So here we can take a glider and run through a system like this and try to understand the overall dynamics. That didn't quite work. And so the next step to avoid Walter Monk's century of undersampling. So the next step is really coordinated robotics. So we're coming into an age where we're moving away from single robot platforms when teams can actually develop the expertise to run multiple vehicles together. So how do we use multiple robots together in tandem with traditional sampling programs? How do we sort of incorporate them into our ongoing monitoring programs to then inform our decisions overall and feed that back to numerical models and validation of remote sensing and all these other tools that we've been using for a bit longer. And so that's really the take home is we're trying to get away from having these be unique standoff pieces of equipment and develop them as tools that we can all use. So to round this out, just to thank, well, first and foremost, all the students that make it possible, and then the partnerships that we have with industry. So a lot of this isn't possible without partnering between public universities and industries such as Teledyne and Rockland and different sensor developers who are usually quite good when you work with them closely to enable new technologies. So thank you very much.
The equipment you're using, those AUVs, how pricey are something in that range, say for the public?
Yes. So an AUV, a cheap one, runs about $200,000. A more common one is usually about $1 million. The gliders are cheap at about $300,000. Between, say, $250,000 to $350,000.
Do you have any for sale?
I don't have any for sale, but I'll happily collaborate.
Thanks, Alex. Similar topic. With the increase in drone technologies, and it feels like some autonomous capacities in our society, prices have dropped tremendously. Are there kind of key barriers that need to get overcome with the autonomous underwater sector to sort of see a change in costs, or is it that the market is just so small and minimal that it's, is there any sort of bleed over effect from these other areas where we see autonomous vehicles really expanding?
So one of the reasons why I feel drone technology has taken off, partly because people want to take GoPro videos of their house. No, I'm being glib, but that's a lot of what's driven down the cost. Underwater, we're limited because we can't get Wi-Fi and we can't get localization. So if anybody ever promises you GPS underwater, it doesn't exist yet. It's still acoustics. They're still using acoustics to get to it. So it's about the cost really comes down to getting your position and knowing where you are underwater. And the technology just hasn't changed yet. And foreseeably, unless there's a major step change in that, it's not going to change in the next decade. So the cost comes down to that. You can build a low-cost AUV, and I've done it with my students where we've built an AUV that goes in a pool for $500 with a PVC pipe and a propeller and an Arduino. You can do it, you can put it in the pool, and you have no idea where you are. And they'll drive around in a circle, it'll come to the surface, and you're like, success. They've learned something. But if you actually want to get reliable, defendable data, that's where the cost comes in. And that's where you sort of see these step changes in cost because of that. That's not going to change anytime soon.
So my old lab actually used one of the PAC-X gliders for long-term transport from San Francisco out to Australia.
Yeah.
And we ran into some issues with fouling and some sensor interference, especially with like turbidity meters and bubble interference.
Yep.
But I mean, since it was such a long transect, I was wondering if had been any, this was back in 2013, so I was wondering if there's been any innovations sort of in terms of the placement of different sensors or sort of the capabilities of these gliders in terms of like long-term monitoring.
So the short answer is I don't think the technology has changed. I mean, for moorings, you're looking at wiper technology to reduce biofouling, but wipers take a lot more power, so then it reduces the range of your vehicle. So when you're trying to do the long-range cross-ocean missions, they're just trying to turn everything off to get as far as they can. And so that hasn't been really changed much there. You do get massive amounts of biofouling in some places. In lakes, knock on wood, we really haven't seen that as a major issue yet. But that's partly because we haven't seen a lot of glider deployments in lakes. To date, there's been our group. There's a group in Minnesota that's been running out in Lake Superior. There's a group in Switzerland that's been playing with sort of small range AUVs. And then there's another consortium that's got together, just got funding this year from NSF to buy 6 AUVs for the Great Lakes, or 6 gliders for the Great Lakes. But it's not something we really have a huge amount of information on yet. It is an issue for sure.
All right, and up next is Elinor Benami from UC Davis. So it's just gonna be here, and then
Hi, everyone. My name is Elinor Benami. I am currently a postdoctoral scholar at the University of California at Davis, and it's great to be here. There's been some really fantastic presentations so far. So today, I'd like to start out by mentioning that the Clean Water Act faces an inspection challenge. So the Clean Water Act is the preeminent water quality regulation in the United States, and within its jurisdiction, it has about 400,000 facilities. In any given year, the combination of state and federal bodies have indicated that they can inspect about 28,000 of these facilities annually, which is less than 10%. In addition, there's a continual threat of decreased budgets for inspections as indicated by these 4 different headlines here from the past years. In recognition of this task, the federal EPA itself has published in its compliance monitoring strategy that they must address the competing challenges of water quality degradation and limited resources with innovative and efficient targeting on the most important environment and inspection challenges. And while there's a series of rules and guidelines and heuristics that govern which facilities are inspected and how frequently, increasing amounts of data available on these facilities allows the promise for machine learning to allow us to identify and distinguish between these different types of facilities that expose us to higher risk. And that's exactly what a few colleagues and I attempted to do in this past year, and I'm going to share some results from that work with you today. So what some of my colleagues and I ended up doing is we pulled down data on the Environmental Compliance and History Online database from 2012 to 2016 on all facilities that are regulated under the Clean Water Act across the United States. We used 36 variables and various configurations of those variables across 3 main categories, those including the facility's location and features associated with their geography, the industry, so both the NICS codes and the 6 codes and the crosswalks in between them, and then the inspection history, so what the outcomes of those different inspections were. We then filtered this down to all the facilities that had all covariate information, and so we ended up with a sample of about 316,000 different facilities across the states. So then what we ended up doing is we ended up predicting the risk. We trained a model on 80% of our data sample and tested this on a 20% holdout sample. So for those of you who are familiar with repeated cross-validation, this is what we were doing here. And so we did this 500 times, and I'm going to show you the results of what our outcomes were in this relationship in between our predicted risk score and the rate of inspection failure. So what you end up seeing is that as you move out to the right, so as you increase in your predicted risk score, your average rate of inspection failure or violations ends up increasing. So now I'm going to show you a series of graphics, and these are each called strip plots. So let's take all of the different facilities that we have in our sample. So that's in these black, in the very black, all of the black lines at the very top. So every single vertical line represents a facility, and where you see this mass and this concentration where it's darker, this just indicates you have a higher number of facilities. So the top line indicates, in black, indicates all the facilities, whether they're inspected or uninspected. And now if you go down to the orange, again, this represents all of the facilities, but only the ones that were inspected in our baseline case. So now here's where the fun begins. So we've predicted out these risk scores, and now we're going to think about how we can reallocate our inspections using some of these risk scores. So in our first case, which is what we call this aggressive national case, we're going to take a rank order list of all our different facilities from the highest risk to the lowest risk, and we're going to assign our inspections from highest to lowest. So if you had, for example, 1,000 different facilities, you would take the highest down until your 1,000 facility inspection budget is exhausted. And here you can see there's this white space over to the left-hand side of your risk score distribution because we're not inspecting any facilities on that side. And you can see that the right-hand side matches pretty well, identically, what our all facilities strip plot looks like up in black. But we know that this is actually not necessarily a very realistic scenario because 95% of inspections are done by states. So here in our aggressive state approach, we take a very similar idea, which is you have a rank ordered list of facilities by highest risk to lowest risk, but then you have state level inspection budgets. So in this case, you see some of this clumping and clustering where you have some of these higher risk facilities, and you also see more inspections that are being directed towards the lower end of the risk distribution. Now, there's another question and issue that you might be concerned about, which is what if facilities learn about what their risk score is and engage in some sort of strategic behavior to then avoid the risk of being inspected themselves. So for this case, we introduced a 1% inspection probability, which is what we call this deterrence component, and we then apply this to our national aggressive scenario. So this should look, and it does look, very similar to the purple case, our aggressive national case, but then you see some more inspections on the left-hand side of the distribution where you have more of these lower risk score facilities. And then finally, in our most constrained case, we keep the state inspection budgets, we keep this deterrence component, and then we add in one more directive from the EPA, which is to inspect all major facilities every 2 years. And the way we operationalize this is that in any given state, we say that they have to inspect half of their major facilities in this given allocation. And the bottom line from all of these different allocations that you can see is as you add in more constraints, you have more rationale for moving down the risk distribution. So to estimate what the benefits are of these different types of reallocation, I'm going to introduce this concept called the reallocation benefit. And how this works is we're going to bin these different risk scores according to the left-hand graphic, which I showed you earlier, which shows you that as you increase in your risk scores, you increase in your average inspection failure rate. And then we're going to assign facilities with a given risk score into those bins. And so we're going to say, okay, if you have this risk score, this is what we expect your violation rate would be, given this is what we found over 500 different random splits of our data set. The bottom line, what we found here is that holding the number of inspections constant, you can use this type of reallocation approach, and we ended up predicting a detected amount of, we ended up predicting a number of violations that were 2 to 7 times the number of violations from your baseline. And that decreases as you increase the number of constraints that you have. So once we published this paper last year in Nature Sustainability, we got a number of different comments and questions from different organizations who were interested in using these types of techniques in their resource allocation protocols. So what I'm going to share with you now and in the next few slides is how we've been thinking about how you might translate this type of model into an actual on-the-ground field trial implementation, and also to solicit your advice and help in identifying a partner who would be interested in participating in a network of organizations trying to do the same thing. So the key question that we're trying to address in this type of approach is where can information about these risk scores actually enhance environmental quality the most? To whom would we provide this information? What are the environmental quality impacts that would ensue from this? And at what cost would these informational interventions come? And after sorting out a number of different types of interventions, our top 2 candidates include focusing in on inspectors and then focusing in on facilities. So in the inspector-based approach, the idea is that we would be providing this risk score information to inspectors among those who are inspecting facilities of similar types of risk scores, and you provide some of them information about the risk scores, and another set you would not be providing information about the risk scores. And there, we would be looking to evaluate how does this information influence their inspection decisions, then what is the risk of the facilities that they ultimately decide to inspect, and then what are the violation rates among those inspected facilities. In the information-based approach to the facilities, the idea is that we'd be targeting a set of high-risk facilities, and to a randomly selected subset of them, they would receive information, and the other set would receive a placebo message. And in this case, there's a number of different things that you can look at. In the medium term, we'd be interested in identifying if there is any stated rationale for changes that they are making on the basis of this information, also seeing what their violation rates are. And then you can also think that in the longer term, you could be looking at how long do these types of effects persist, so the durability of them, as well as what some of the spillover might be to other facilities that are high risk that do not participate in the intervention, as well as what some of the spillovers might be to other facilities that are at the lower end of the risk distribution. So if we're concerned about this strategic behavior before, we can actually look at and evaluate that in this case. So as we've been thinking about these 2 different options here, I'm providing a matrix that we've been using to systematically try and identify and evaluate what are the different learnings we would gain from these 2 different types of approaches. And this basically groups down into the costs on the left-hand side, and then the other categories represent the potential benefits. And while I have talked about these 2 different interventions in contrast to one another, in reality, you might actually think that they could be complementary interventions because providing information and then enhancing the credible threat of an inspection could work more effectively than either one in isolation. So at this point, we are very interested in learning more from other organizations about how they can use this type of approach in their field implementation and in their protocols. And basically what that boils down to is 3 main things. One is we're looking for partners who are willing and interested to explore how this can affect their resource allocation protocols. Second, who have access to facility inspection and violation history. So this need not be just Clean Water Act, it can be other types of inspection protocols as well. And that have some facility feature data that allow us to distinguish in between different types of facilities and their risk types. This would be an exchange of information among a series of different governing bodies who are interested in learning how machine-based predictions can inform their regulatory performance. And this is a network of individuals both at UC Davis as well as at Stanford, where I did my PhD. Great. So in summary, Our model predicts 2 to 7 times the number of violations for the same number of inspections. But as we think about moving this from a model to a field trial, we are interested in finding out where does providing this risk information influence decisions, strategic behavior, and ultimately violations and environmental quality. So we're looking for partnerships for field trial. I know we're coming up on a break. If you are interested or know folks who would be interested, please come reach out and find me and talk to me. And in the meanwhile, thank you all very much for your time and happy to take questions.
Hi, I'm Greg. Nice to meet you.
Nice to meet you.
Thanks for the presentation. So have you looked at any of the California-specific data sets, and are there issues that you could say would be necessary to overcome before we even considered a project?
I think that's a great question. I think the 3 main criteria so I will take one step back and say when we were approaching this project originally, we were in several conversations with the federal EPA who had suggested that they had some questions about several different states having varying degrees of higher and lower data quality. But in some cases, that can actually be an advantage because you can then, if you're able to flag, these are places where we know we have higher quality and these are places where we know we have lower quality, you might actually be able to leverage what you're able to find from the places that have higher quality to those that are lower quality. So I think there's actually opportunities. It depends on the specific data sets, but there are actually some really neat opportunities that you can explore through having that type of variation. Yes, please do. Okay.